Just 1 or 2 minutes after 1:30.
Okay. And when do you want me to stop?
Well, it's usually a good idea to leave, say, 10 minutes for questions. So,
Okay.
of course, I've always found that if I make the talk about 10 minutes shorter than expected, everybody thinks it's a great talk. Did you get much snow out where you are? Because we didn't get any where I was north of the city.
Oh, I think we have a few inches.
Hello, everyone. My name is John Raymond, and welcome to the Center for Astrophysics Colloquium. This is a completely virtual colloquium for the first time in quite a while, not because of COVID, but because of bad weather forecast for the region. Those of you on Zoom will be able to ask questions via the chat at the end, and those of you on YouTube can put questions into the Q&A function. So I'm pleased to introduce today's speaker, Ramesh Narayan from the Harvard Astronomy Department. He got his PhD at Bangalore University and worked for a couple of years at Raman Research Institute, then went to Caltech for a postdoc where he and I believe Lars Hernquist and last week's speaker, Roger Ramani, were all postdocs with Roger Blandford. After that, he went to the University of Arizona for a faculty position and came to Harvard in 1996. Of his numerous awards, I'll just mention that he's a fellow of the National Academy of Sciences and the Royal Society, and that he got a Presidential Young Investigator Award quite a few years ago. I first met Ramesh at a meeting on cataclysmic variables at a time that he was working mostly on scintillation of radio sources as a way to diagnose the density fluctuations in the interstellar medium and on gravitational lensing. But he quickly turned his interests to accretion He wrote a couple of papers on accretion and cataclysmic variables, but very quickly went into black holes. And he's had a long and fruitful collaboration with Jeff McClintock, in which they measured the spins of high accretion rate black holes from the X-ray spectra. But today he's going to tell us about the stuff he's been working on mostly in recent years, which is accretion on low accretion rate black holes. Ramesh.
Thank you, John. Thank you for that introduction, and thank you, everyone, for showing up on this stormy day. Yeah, this is going back to a few years ago when we were all doing this during COVID. Kind of feels familiar. So yeah, actually, I've been now at Harvard for 32 years, member of the CFA, and the topic I'm going to discuss is something I started working on pretty much within a couple of years after getting here, this hot accretion flows that I'm going to describe. So today's talk, I'm basically going to kind of review this story, this field, with an emphasis on what our group here has been doing. And this is a topic that just keeps on going. It's still quite active, and I will show you what's been happening more recently. So, I haven't given many CFA colloquia. I think I gave my job talk as part of the Colloquium series before I got here. I gave the talk on black hole spin, the topic that John mentioned. That was the work that Jeff McClintock and I did for several years. So I kind of summarized that. And today I'm going to summarize this other topic, which has been with me now for 30 plus years, hot accretion flows. Okay, let's start with accretion flows. So I need to figure out how to, yeah, good. So here are artists' impressions of what accretion disks might look like. So there are two major classes of accreting black holes that we know of in the universe. Active galactic nuclei, the picture on the top left. So these are, as you know, the supermassive black holes in the nuclei of galaxies who are accreting gas. Gas is generally supplied from the surrounding medium, and it's the usual story. Gas comes in with angular momentum. It spirals into the center, converts a good fraction of the energy released into heat, and finally radiation, which we observe. Very bright sources, as you know. Then we've got little black holes, typically in our galaxy. That's where we see them. They are, several to several tens of solar masses. And some of them get gas from a companion star. Same story again. Gas goes around, spirals in, gets hot. And in this case, they shine as X-ray binaries, bright in X-rays versus the supermassive black holes, bright in optical UV. So this is the artist's impression. Now, even the artist has shown here these linear things sticking out. Those are the jets. And jets are pretty common in both of these classes of objects. And in the case of jets, we actually have real images. We don't need an artist any longer. We can resolve them. And I've shown a few famous jets here. Cygnus A, then A, Virgo A, or M87, which I will be talking more about as I go along. So these are all typically seen in radio, where we have the best images, but also in optical, X-ray, etc. And seems to be part and parcel of the whole accretion story. So that's the background, the field. And what I'm going to do in today's talk is, it's a very limited agenda. I'm going to put more emphasis on the theoretical concepts. Then I'm going to say a little bit about numerical simulations, and time permitting, what's next. I'm guessing that 2/3 of the time will be on the first bullet, 1/3 will be on the second bullet, which means there will be no time for the third bullet, but we'll see how it goes. So let me start with something that everybody knows, the famous thin accretion disk model. Developed, in fact, exactly 50 years ago, 1973, Shakura and Sunyaev, Novikov and Thorne, etc. So this is a model in which gas that's accreting around the black hole is geometrically thin. So we are looking, this picture is a cross section. So the vertical thickness of the gas configuration is small compared to the radius. And that allows a number of simplifications. And you can write down nice, beautiful equations to describe the whole system. And what you find is that a system like this will, when it accretes around a black hole, will release about 0.1 m dot c squared of energy into heat. M dot is the mass accretion rate, grams per second. C, of course, speed of light. So 10% of the rest mass energy typically is released. It can be a little bit less or more depending on parameters, but that's a good number. And the feature of this model is that all that energy is radiated. So we call this a radiatively efficient mode of accretion. And this parameter eta, radiative efficiency, is 0.1, 10%. When you work out this model, one of the things you find is the gas is optically thick. So for instance, here is a little order of magnitude estimate. The electron scattering optical depth through the disk, vertical direction, is on the order of 10 divided by Eddington ratio, where Eddington ratio is the actual mass accretion rate in units of the Eddington mass accretion rate. And Eddington rate is defined as the rate at which, with 10% efficiency, you will radiate an Eddington worth of luminosity. Okay, so if you're at Eddington accretion rate, this guy has got an optical depth of 10. And notice the inverse relationship. As you go to lower and lower m dot, your tau becomes larger and larger. So the system is more and more optically thick. The lower you go in m dot, the thinner it gets, etc., etc. And the beautiful simplification then is, it's an optically thick gas. It's going to produce more or less a black body-like spectrum. And you can now compute what the spectrum should look like. In fact, it'll be a black body at each radius with the peak frequency evolving as a function of radius, but most of the luminosity comes from the center. And so the radiation you observe is going to be dominated by a temperature of this order given in this bullet. So for a 1 or 10 solar mass black hole, you're going to be at 10 to the 7 K, roughly. That's a KeV. Whereas if you are an AGN, say 10 to the 8 solar mass black hole, 10 to the 5 K UV. And this is very nice. This is exactly what we observe from X-ray binaries and quasars. And so, in fact, I will show that here, a couple of slides. So here is one famous X-ray binary, LMCX3. And this shows X-ray data, all this beautiful data here. And the orange line is a thin disk model fitting this data. Now, ignore the fall in the observed flux at low energies. These are all absorbed by the ISM. The peak is all, I think, coming through without much absorption, and it fits beautifully. This is the, it's a 2 keV peak, exactly like Shakura and Sunyaev said. And in fact, you can fit it beautifully to this model. There's some little extra hard X-rays, but that's tiny compared to the peak emission. Here is a plot from this famous paper by Martin Elvis. The solid line here is a kind of an average quasar spectrum. So you take all the bright quasars and redshift them properly to redshift 0 and then add them up. And the dashed line here is sort of what the thin accretion disk model would predict, a black body-like spectrum. And the guy peaks, of course, at UV, 10 to the 15 hertz. So, and you can see that this is the nu plot. Most of the luminosity is coming out in this peak. That is the so-called big blue bump, and it works great. Okay, so the thin accretion disk is a lovely model. It works well for many systems that we observe. But there is also a problem. When you look at systems in the universe, anytime you go to some object which is less than, say, 1% of Eddington, it never looks like the thin accretion disk. I mean, there may be an exception to what I've written here in the second bullet, but I'm not aware of any. As far as I can tell, The moment you're below about 1% of Eddington, it looks like the thin disk is out of the window. Something else comes in. And that something else seems to be very hot gas, more than 10 to the 9 degrees Kelvin. So let me show you some spectra here. Here are two X-ray binaries. This is LMCX3, what I showed you earlier, a beautiful black body or multi-temperature black body spectrum. Here is GRA JO422. Here's the spectrum, and you look at first sight, you say, look, oh yeah, it's another black body, but this is 100 keV. You can't have a 100 keV black body because that would be brighter than the whole galaxy, right? L goes like T to the 4. 2 keV is perfect. You get an Eddington or 10 to the 38 ergs per second system. This guy is impossible. This is not black body. In fact, this is the Comptonized spectrum. You need gas of 100 keV temperature, 10 to the 9 plus. And we actually have X-ray binaries that flip between these two states. The same guy. One day it may look like this, and one day it may look like this. So clearly, accretion can do something different from the thin disk. Another example would be our own galactic center, Sagittarius A star. Here is the spectral data that we have. This somewhat old plot. There's a little bit more now, but in any case, where the big blue bump should be, there is really no evidence for any radiation there. It's a slightly tricky question because this is the region of the spectrum that is absorbed by our ISM. But if we had a thin disk, there would have been a huge amount of infrared. In fact, the peak would have been off scale in this picture, and the infrared would be booming. We don't see it. So it's obvious that our galactic center is not like, Martin's quasars. It's something different. Okay. So what is going on? Now, here's the problem. You can go and look at Shakura-Sunyaev. That model becomes more and more consistent as you go to lower m dot. Low accretion rate, low luminosity is when it is most optically thick and ought to be working perfectly, but nature doesn't like that solution. Fortunately, people found other accretion solutions which violate the assumptions of Shakura-Sunyaev, and I'm going to call them hot accretion solutions. They've given other names. So for instance, first when we got into this game, we called it an advection-dominated accretion flow, ADAF. But for today's talk, I'll just call it hot accretion. So here are some of the key papers. I think this is truly an important paper, Shapiro et al., Shapiro, Lightman, Erdely. They introduced the idea of a two-temperature plasma, and I will talk about that. There was this completely ignored, forgotten paper by Ichimaru in '77 that nobody knew about until after we came up with our story. Then they dug the literature and found this paper. There is a paper by Rees et al., which kind of lies somewhere between Shapiro et al. And the new work. And then I'm going to talk about what happened with the things that we added to the story. Okay, so we want a hot accretion solution. So I'm just going to kind of lead you through the logic here. Let's assume that somehow, by hook or by crook, we managed to get them a maximally hot accretion disk. That really means you have an accretion disk with virial temperature. And for gas around a black hole, ordinary, solar composition gas, virial temperature is 10 to the 12 Kelvin divided by R, and the R is radius in Schwarzschild horizon units. Okay, so close to the black hole, 10 to the 12 K. So I'm saying, let us imagine we have a disk with gas temperature equal to virial temperature. What do we expect? Because the temperature is so large, of course, the gas is going to have a large pressure. Large pressure means it can no longer be a thin disk. In fact, this will be a geometrically thick disk with a vertical height of the same order as the radius. Okay, so it's going to be quasi-spherical or big fat torus, something like that. Now, here is a step that I won't try to actually support. Just take my word for it. By the time you go to a large scale height, you will find that the radial velocity, the inflow velocity of the accretion disk, will be much larger compared to the thin disk. So if you have a large radial velocity, and let us say you keep the same m dot, which you had already for your thin disk model, because the velocity is large, the surface density will become small. So this will be a model in which the vertical surface density will be a lot less compared to the thin accretion disk. And in fact, now you can calculate what is the optical depth. It turns out that for a model like this, the optical depth is of order 30 times Eddington ratio. So you can see, once you go below 1% of Eddington, if F-ed is 0.01, your tau is going to be less than unity. This is electron scattering tau. I mean, there's also the emission and absorption and Planck capacities, etc., which will be even lower. But this is clear. This is going to be an optically thin medium. So, one of the key simplifications in Shakura-Sunyaev is gone out of the window. No more black body. So that's good news. So once you go to below 1%, tau is less than 1, no black body, at least looks promising. You got hot gas and you don't have black body radiation. Essentially what I'm saying is if it was trying to radiate like a black body, it cannot be at 10 to the 12 Kelvin. It'll radiate like crazy. In fact, even if it's optically thin, you can show 10 to the 12 Kelvin is much, much too hot. Electrons will radiate, amazingly huge amount of luminosity, and the temperature cannot be sustained. So, it's all beautiful, but why would this be relevant for nature? This is where Shapiro, Lightman, and Eardley came along, and they came up with this key idea. Perhaps the accretion gas is a two-temperature plasma, where the ions are basically the atomic nuclei, and here it's mostly protons and alpha particles. So the ions are virial, okay? So we will retain that aspect of the model, but the electrons are no longer tied to the ions. They can do their own thing, and the electrons will be cooler. So they will radiate less. In fact, they will adjust their temperature so as to satisfy all the energy requirements. So once you break the connection between ions and electrons, a virial model is no longer out of the question. You can adjust the two temperatures so that you are virial and you have all the good properties, including low optical depth, low surface density, etc., and still satisfy energy requirements. There's one other thing this model has got. If you ask, why would a normal ionized plasma have both ions and electrons with the same temperature? It's because, thermodynamically, that is the, maximum entropy state. But in microphysics terms, there are collisions between particles, so-called Coulomb collisions. And the Coulomb collisions is just, electrostatic interactions. Exchange energy information between the two species, and they come together and have the same temperature. But the speed or the rate at which Coulomb collisions happen depends on the density of the gas. And my, virial model has such a low density that Coulomb is no longer effective. Completely different from the thin disk. In the thin disk, you've got a high density. Coulomb is extremely efficient. You never can split the two temperatures, but here you can. So this is again self-consistent. The large assumed Ti gives you a low gas density, low Coulomb collision rate. Therefore, ions and electrons can afford to have different temperatures. With one big assumption here, that the only way they communicate is through Coulomb collisions. Who knows what other ways they might communicate. So here is a little flow chart to show this aspect, the Shapiro-Lightman-Eardley part of the story. So you've got an accretion flow. It produces heat through viscous dissipation. And some fraction of that heat goes into the electrons, some fraction goes into the ions. Ions don't radiate. Electrons are the ones that have to produce all the radiation, so they're going to cool. If these two guys are coupled to have the same temperature, then they will both cool. Through Coulomb collisions, the ions will cool, and then the electrons will radiate, and you'll get the thin accretion disk. It'll be a one-temperature plasma. It'll be cold and great. That is Shakura-Sunyaev. If you go to this other regime, where your density is so low that the Coulomb collisions are no longer effective, then what can happen is the ions will just hang on to whatever energy they receive. They will go pretty much to virial temperature. They will give you your pressure. They will cause all the effects I talked about. They don't radiate. They don't lose energy to the electrons. There's nothing else they can do. They just remain virial. And the electrons, meanwhile, take whatever energy they got. They produce the radiation you observe. And the whole thing is self-consistent. So that's the beauty of the SLE solution, Shapiro-Lightman-Erdely. Good. So this looks like a very nice model. This, as you can imagine, works best at low accretion rates because you want to have a low density. And it seems to satisfy everything we want with one big bad news. It's unstable, unfortunately. It's thermally unstable. That is, you can set up, can solve the equations, get a solution. And if you perturb the temperature the slightest bit, the system will run away. If you cool it a little bit, it'll just collapse all the way and become a thin accretion disk. If you perturb it up a little bit, it'll just go off and go beyond virial and just blow up and basically, disappear as a solution. So this, in fact, pretty much put a damper on the model. I mean, this result about instability came very soon, immediately after the model was published. Ichimaru actually had the solution. Nobody paid attention. And certainly we had no idea of this paper when we did our work. And then we came along. This was Narayan and Yi, 94, 95, and then Marek Abramovich and company. And basically we showed, look, SLE got half the story right. 2 temperature, great idea. But you need to do a little bit more work. There is yet another hot solution. And the second guy is stable and is the one we want. And just to cut to the chase, I'll go into the concepts in a bit. This model, I think, is the one that right now is the only one that seems to be a useful description of low luminosity AGN and X-ray binaries, all the guys with temperature about 10 to the 9 Kelvin. I will not go into the technical details here, but I'll just tell you what was the thing that happened here, what we added. Right, Shakura and Sunyaev had one set of assumptions and equations. They found one solution. Shapiro broke the equality between ions and electrons, and that immediately showed up a second solution, which unfortunately was unstable. We had to break one more assumption, and this is the, I'll just say it in symbols. In the usual disk theory, people assume that whatever heat you produce is lost to radiation. So Q plus is the heating, and you say it's equal to all the radiation that comes out, Q minus. So these would all be radiatively efficient solutions. But it doesn't always have to be the case. You can ask, what about if the gas cannot radiate? And that's really what we need, right, in these virial things. At least ions are not radiating. Then it turns out that you have to modify this equation. You get another equation with an extra term. And what is more, this extra term is a kind of like it takes an algebraic equation, makes it a first order differential equation. Bottom line, it shows up a third solution. So we had Shakura Sunyaev, SLE, and now this is new guy, which we called ADAF, advection dominated accretion flow. I'm just going to call it hot accretion flow, which kind of we kind of introduced in a review article. And just like SLE solution, this guy appears only at low Eddington ratios. So it's very nice. This is kind of appears to be the answer. This is a picture I just pulled out of our 95 paper. And there are lots of assumptions here, but this just shows the topology of these solutions. This is mass accretion rate in the bottom. Eddington is out here. This vertical line is 10 to the minus 5 Eddington, and so on. Vertical axis is ion temperature. So this solid line here is Shakura Sunyaev. This is the thin disk. And in fact, over this branch, ion and electrons have the same temperature. Once you untie those two temperatures and let them go free, you get the SLE solution. 2 temperature solution. This is this guy. It gets a lot hotter, but it's unstable. Then you do the second modification. You add advection. And then you find that there is a third solution. The SLE really didn't know what happens above here. They basically said the system will blow up and disappear. But in fact, no, there's a third solution, which is dominated by advection. And this, we think, is what's happening in all of these low Eddington ratio systems. In fact, this nose, which we don't know how to calculate precisely, I think is at around 1% of Eddington, so around here. And once you go below that, this solution appears. And apparently, this is what nature wants. Okay, so it's a radiatively inefficient solution. I won't talk too much about that. The beautiful thing is it only appears when you come to low Eddington ratio, precisely where nature is telling us something new is needed. Okay, good. I'm not going to show this slide. Okay, so I'm going to say this is very nice in the following sense. You know, most black holes in the universe have low luminosities. Nice to know that we understand them in quotes. At least we know, or we think, if the model is right, they're very, very hot, they are 2 temperature, all that good stuff. But the 2 temperature is a problem. You know, you need to have a lot of faith to think that you can have plasma with ions at 10 to the 12 Kelvin and electrons at 10 to the 10 Kelvin, 100 times difference in temperature. Okay, even if Coulomb collisions don't bring the temperatures together, it's a magnetized plasma. Magnetized plasmas, as you know, all the fusion people know, they have, they have a life of their own. You can't control them. So you would think one way or the other, the ions and the electrons will come together and reach a common temperature. Well, we do have exceptions. The solar wind, I am sure there are many experts, starting with John Raymond, who understand the solar wind well. And there we know that it's possible to have 2 temperatures. But this is still a non-relativistic plasma. When I go to these relativistic plasmas, anyway, even though, my group kind of pushed and invented this model, we have always been very, very suspicious whether 2 temperature is really possible or not. If it's not possible, the whole model just disappears. Should we trust this model? This is where the Event Horizon Telescope comes in, EHT. I don't have to explain this to anyone here. This is the EHT image of M87, the black hole in M87. This is our galactic center, Sagittarius A star. And, we had a lot of hoopla, there is polarization, etc. This fellow actually, and I'm going to convince you of this, has told us that this hot accretion model probably is close to the truth, in the sense that it is consistent with everything that model predicted. So let's start with some of the things that it has confirmed. The model says the plasma has to be optically thin, electron scattering pretty optically thin, and which means you should be able to see right all the way through the gas in the accretion disk. And I don't have to tell you, the fact that we saw a ring and a shadow, and maybe one of these days we'll even see the so-called photon ring, the narrow feature here that we believe is in there. To see all this, you better be able to see through the gas. It's clear that Sagittarius A star and M87 have optically thin gas around them. Great. It's not a thin accretion disk, not optically thick. The model, I didn't show the slide, Sagittarius A star was modeled. It's the very first guy we modeled in 1995 using the ADAF model. And so, we had predicted that the ions will be 10 to the 12 Kelvin. Electrons, I think we said would be about 1.2 10 to the 10 Kelvin. With, of course, big error bars, right? I mean, this was an early model, 1.2 10 to the 10. There was also a model somebody else made for M87. What does EHT tell us? Now, EHT actually measures brightness temperature, right? This is what radio astronomers do. They measure brightness temperature anytime they have an actual resolved image. So in these images here, the color scale shows the brightness temperature. Sagittarius A star, the brightest regions go up to 13 times 10 to the 9 Kelvin or 1.3 10 to the 10 Kelvin. Let me remind you, brightness temperature for ordinary thermal sources is a lower limit on the electron temperature. The electron temperature or gas temperature could be a lot higher. In these particular objects, I think we can plausibly argue that it will only be higher by a factor of a few. So probably, most likely, Sagittarius A star has electrons at 5 times 10 to the 10 Kelvin, certainly not below 1.3 10 to the 10 Kelvin. And that's exactly the ballpark of what the hot accretion solutions are predicting or predicted 30 years ago. And M87 looks a little bit cooler. Again, it's a lower limit, but the lower limit is 5 times 10 to the 9 Kelvin, but definitely on the hot end. So this is wonderful. This is direct, there's no modeling here. You're just measuring something and saying, I know that the electrons are hotter than such and such. I would love to be able to tell you that we can also confirm the 2-temperature plasma, that the ions are even hotter. I don't know how to directly measure ion temperature. You have to fold in a model, and this is what the EHT team did. They put a lot of modeling details, and they ended up with the conclusion that this needs to be a 2-temperature plasma. If the ions were also the same temperature as the electrons, you just can't explain the EHT data. So it's a little bit indirect, model dependent, but it seems to be consistent with the 2-temperature feature of the model. This I decided not to talk about. These are radiatively inefficient. We have direct evidence now from the EHT that Sagittarius A star, for instance, is radiatively inefficient. Good. So what have we achieved? When we have a model, it requires certain strange features like a 2-temperature plasma, virial temperature, etc. We finally had the opportunity to directly test some of these things using the EHT. And fortunately for us, or maybe, it was our day, everything that we thought should happen seems to have happened, and the model seems to be more or less hanging together. I'm not going to claim victory yet, okay? There may be some more twists to think about. Right now, as far as these models go, we have to now talk about what is the role of magnetic fields. I'm going to come to that as I go along the last bit of my talk. Any uncertainties in the fluid dynamics? Where do jets come in all this? Well, what about winds, convection, etc.? There's an enormous game to be played with plasma physics. How do you actually heat the particles? What are their properties? And a question that I'm not going to talk about. We have 3 solutions, remember, at these low Eddington ratios. You throw away the middle guy, SLE solution, it's unstable. We still have 2 stable solutions, thin disk and this new guy, the hot accretion. But we don't see the thin disk. The moment nature sees there's a hot solution available, it jumps there. Or at least that's what it looks like. I would love to see exceptions to that claim. But in any case, it looks like the vast majority of them go to the hot solution, even though Shakura Sunyaev is still valid. That is a beautiful problem. Some beginning has been made by Herin Cho in her first project here as a student. But yeah, we'll see where that goes. I'm going to now talk about numerical simulations. And this is a field that has really come along really nicely in the last 20 years or so. These hot accretion flows are particularly well suited for simulations. Firstly, they don't radiate that much. They're radiatively inefficient and they're optically thin. So because of that, you don't have to worry about the radiation. You can ignore radiation more or less and still get roughly the correct answer. So you can just do gas accretion, MHD. The large temperature, virial, means that you've got a big fat system, large scale height. And those are the best systems for numerics because the thin disk is horrible to resolve it on the computer. You need tiny, tiny cells, and that kills your computer resource. Big fat disks are great. You do need to work a bit hard. You need to put the general relativity into it, but that's okay. people have succeeded. I'm going to just focus on one aspect of simulations. I'm going to run a couple of simulations here. So what we are seeing here is black hole accretion on the computer, hot accretion. The black hole is in the left, the middle of the vertical column. That little circle there, the white circle, that's the black hole. The colors represent gas density. And we are looking at a so-called poloidal slice. So this is the vertical axis here is the rotation axis of the accretion disk. And the gas is going round and round this vertical axis. And these are two different simulations with different conditions. I'll talk about that in a second. And what you're seeing here, as I said, is density in this vertical slice. And the lines are magnetic field lines. So the guy on the top left, is what I would say a typical standard accretion disk that most people would recognize. It's a turbulent system. You can see how the magnetic field lines are all twisted into loops and doing, it really just looks like any turbulent system with embedded magnetic fields. The guy on the right was started with the different initial conditions. And what you have is field lines that are all threading in the vertical direction. Just look at this guy. Every one of these is a field line. This is the black hole here. Whole lot of vertical oriented field lines. In fact, these field lines are going to infinity, both above and below. So they are long, elongated field lines cutting through the disk and, certainly changing. You can see that the pictures look completely different. This guy is quite different dynamics. And this is the guy I'm going to focus on now. This is called a magnetically arrested disk, or MAD. The idea is the magnetic field here is strong enough to actually push the gas. And so it's a tug of war between the gas, which is trying to fall into the black hole, and the magnetic field, which is pushing it back. So it's a magnetically arrested disk, as against the picture on the top left, which is a non-MAD system, where the magnetic field is weaker and just goes along with the gas. It doesn't have a will of its own. So this magnetically arrested disk was something that Igoumenchev, when he was at the CFA, discovered as part of his simulations, something that nobody had seen before. And we even figured out why. They had the wrong boundary conditions. So anyway, Igor did the right simulation, and he found that this thing appears that under appropriate conditions, magnetic field can be pulled into the black hole. It can collect around the black hole, and then it's pinned in there. It's strong enough to start pushing back on the disk, but the disk is strong enough to push its way through the field, and they reach an uneasy truce. This is the magnetically arrested state. And as you can imagine, with this strong magnetic field, which is nicely confined around the black hole, these guys make fantastic jets. And that was the discovery of Sasha Tchaikovsky when he ran one of these MADs with proper GR and everything, and found amazing jets coming out of these systems. Okay, so let me just show one more movie here to kind of illustrate one other point, exactly what is going on with these magnetically arrested guys. So the guy top left is a non-MAD system. The bottom is a MAD system. So let's see if I can stop it here. Yeah. Okay, so see the difference. Okay, once again, color is density. And the MAD system, all this red stuff is density unity, and all this green stuff is below 1%. So there's a factor of 100 contrast between the red and the green. So the disk, black hole is in the middle. The disk is trying to accrete. The gas is accreting. It's coming in, but it's not coming in a more or less axisymmetric way as the guy on the top left. Here, the magnetic field is imposing its will, And in fact, what's going on is these green patches, they are full of magnetic field. It's a whole bundle of field lines which are trying to escape from the black hole. So they are floating up. This one, this one, this one. And if I let it run, you'll see more of them appearing from the center. They're trying to escape. Okay. Meanwhile, the gas is coming in along these little streams. And so this is this constant non-axis symmetric push and pull between the accreting gas and the escaping magnetic field. And what we and others have found is this guy is pretty common in simulations. It almost feels like it's unavoidable, that this is the natural end state. It is also the maximum field that you can hold around the black hole, because you've now reached the point where if you try to put more magnetic field, it'll escape. It's trying, right? It's trying to escape all the time, and if you reach the saturation limit. And when you work out, how does jet power work? Jet power, you can show, scales as magnetic flux squared, black hole spin squared. So you need a spinning black hole. Then you just want to maximize this flux. And the MAD is when you maximize it to its limit, the saturation limit. You get the strongest and quite amazing jets. Great. Okay, so that is nice. Repeating what I said, what Tchaikovsky showed is MAD is great, makes relativistic jets. You can calculate the power in the jet. And then the question is this really relevant for us? Really nature, does nature go into this MAD state or not? Are the AGN and X-ray binaries in which we see these powerful jets, are they in this MAD accretion state or not? This looks like an open question. Let me not show this movie. Once again, EHT comes to the rescue. Turns out that M87, where we have more data currently because there's polarization as well, the polarization in particular seems to suggest, more than suggest, strongly indicate that M87 is in the MAD state. The magnetic field lines are strong, they are rigid, they're kind of, squeezed around the black hole and sticking out. In fact, I should mention, the most powerful diagnostic for making this conclusion is one that Daniel Palumbo has developed as part of his PhD research. Okay, so it looks like M87 is MAD, and that's great because you know that M87 has a jet. There are all these beautiful radio pictures of the jet. It's one of the nicest nearby relativistic jets to our galaxy. EHT work, and also work by the gravity interferometer, seems to suggest that Sagittarius A star probably is also MAD. You can immediately jump up and ask, but Sag A star has no jet. What's going on? I won't go into that now. Let's just say EHT says Sag A star probably is MAD. EHT says M87 star very likely is MAD. I'm just going to make a leap from this. I'm going to say, look, 2 out of 2 objects that EHT looked at look like they might be MAD. So why don't we say that any object that has a hot accretion flow in the universe is probably MAD? It's in the MAD state. So is that so crazy? I think it's not so crazy, and let me just make this point available. Clarify this point. So here is my, artist's picture of what MAD is. You've got all this bundle of field lines around the black hole. There is accretion happening. And you can ask, how much flux do I need here, magnetic flux? How much do I need to reach this MAD state? Remember that the black hole is very, very tiny. The gas is coming from, 10 to the power of 6 black hole radii. That's the ambient medium in the galaxy. Out there, you may not have a lot of magnetic field, but you've got a lot of area. So magnetic flux wise, what's out there is orders of magnitude more than what you need. So I would say you only need to get a little bit of that field down to the black hole and you'll reach the mad state. In fact, in my opinion, it's hard to avoid mad state if you accrete for any length of time. You'll always reach the mad state. And once the field has accumulated, how do you get rid of it? Right? This guy is trying to escape, but the gas is constantly pushing it in. The only way to cancel this is by sending in field with the opposite orientation. Then you can cancel it. This line cannot escape, but this line can reconnect with another line which comes with the opposite direction. And then you can maybe bring the flux down to 0. But then, why would it just bring enough flux to cancel without overcorrecting? Because what I would say is, okay, it'll keep bringing lines with the opposite sign, and it'll still be mad, except the field lines will be pointing down. So basically, my argument is that it's very hard to avoid mad. I think mad is probably the natural state. We have two objects for which we could have tested, and they are mad. So here is my summary of the messages that I wanted to convey here in this talk. When you go to low accretion rates, below about 1% of Eddington, and the exact value is uncertain. It depends on things like the viscosity alpha parameter and, the equilibration of temperatures, and, leave that aside. On that order, 10 to the minus 3, minus 2, maybe even 3%, okay? When you reach this regime, it looks like you can make two statements with some confidence. Accretion is hot, and here hot means close to virial temperature and correspondingly to temperature. Ions are close to relativistic temperatures. So about 10 to the 9 Kelvin, maybe even about 10 to the 10. Second lesson, I believe this, but this is yet to be established. I think all these guys have mad accretion. And the beauty of mad accretion is that is a system in which the magnetic field is the strongest it could possibly be for a given accretion rate. And therefore, the jet will be the strongest it could be for that accretion rate. And Tchaikovsky's work and other people's work has shown once you get to this mad state, especially if your black hole is spinning rapidly, you can get huge efficiencies in terms of jet power. We talk about quasars being, great engines. They produce 10% of the accreted mass into luminosity, okay, 10%. These mad accretion disks can produce 100% of m dot c squared into jet power. I don't know how that is then converted to radio waves, non-thermal electrons. That is somebody else's problem, but just the raw power is something we can now estimate. And so I will just stop here because I think I am at the 50-minute mark. I think there are some things that we can do now in the future. We are close to actually contributing to some important problems. So for instance, in the whole feedback game, where AGN feedback does things to galaxy formation and evolution, the coupling between the galaxy and the black hole is via accretion and then wind or jet or whatever coming out and radiation. And at least the radio mode or maintenance mode feedback is entirely in this hot accretion mode. We now have a handle on these guys. We can actually estimate how much power comes back in jet. With a little bit of work, we can make a distinction between jet and wind. We can say how these things depend on parameters, accretion rate, spin of the black hole. We can talk about how mass and spin evolve as you accrete. Once you say it's mad, these are all absolutely predictable and calculable. And these could all go into cosmological simulations. They could go into people who do population studies, etc., etc., etc. I won't dwell on this. There are still a few loose ends, actually some real big loose ends. The bottom bullet here, and I'm hoping that here in Cho will at least make a beginning at solving this as part of her thesis work. For the rest of you who don't care about feedback but still would like to understand accreting black holes, you want to calculate luminosity, spectra, etc. for the low Eddington ratio black holes, I think the situation is a little bit more murky. If the gas remains thermal, that is, the electrons have thermal, even though two temperature, but if they're thermal, I think we can calculate stuff and actually do something. But most likely, there is a good population of non-thermal electrons in these systems, even in the accretion disk and definitely in the jet. That is a big problem. At least I don't see an immediate way of cracking open that problem. So I will stop here and leave this as my summary slide. Should I look at chat or something?
Yes, anyone with questions can type them into the chat.
There is a hand raise. Should I look at that as well?
Sure.
Yeah, Chief Fung.
Yeah, I have a question. Thanks. You mentioned that ions, the radiation is not important for ions. I just want to ask why, because there are photons and there's magnetic field. Why don't ions lose energy through photon hadronic processes or synchrotron? And does that mean like these systems aren't neutrino sources?
Yeah, it's a good question. So normally when we talk about radiation, we are talking about synchrotron radiation, which dominates in these systems, or Compton scattering, which pumps photons to higher energy. These processes, their cross-section and are very heavily mass dependent, particle mass dependent. So you can easily verify for yourself that for a given magnetic field and given number density of electrons and ions, even if the electrons are hotter, the synchrotron emission or Compton scattering will be very much favored by the electrons, and the ions will hardly radiate at all. Okay, so the standard processes really don't, ions are totally irrelevant. So you're asking about maybe hadronic processes, where photons maybe can interact with the protons or alpha particles, produce pions and all sorts of stuff, or the protons can collide with each other. Those processes, again, turn out to be quite unimportant for the simple reason that the density is too low. So in the early days, when we made our ADAF models, actually our densities were higher. And at those densities, it was borderline. We could kind of convince ourselves that maybe, the galactic center could produce gamma rays from pion formation and pion decay, etc. But I would say current models, and the current models are informed, for instance, by the EHT and other work, their densities are too low. And our best estimate is that these other processes do not matter. I wish they did matter. I will tell you this, because if those channels were available, that would give us a direct handle on the ion temperature. And we would be able to actually, through measurements, verify that we got a 2-temperature plasma, virial ions, etc. I hope it happens one of these days. But I would say at the moment, the models suggest ion processes are not important.
Thank you.
John, you have a question here. What mechanism dominates the dissipation of kinetic energy, and does it favor ions or electrons? Great question. This is an open question, as you can imagine. We really don't know how dissipation works. I think we can say that it is unlikely to be shocks. The turbulence and the motions are all, I would say, subsonic. There are no shocks. Reconnection is a highly favored mechanism. So you could have reconnection when occasionally magnetic field lines with the opposite polarity come and meet and annihilate each other. And people are studying this using plasma codes. Reconnection could also appear as part of turbulence, because turbulence has eddies going round and round, and then they can reconnect at some level. By the time you come to mad accretion, the turbulence is kind of less important, it seems. It's all these bundles of field lines moving up and down and fighting with the gas. And there, I think reconnection probably is a pretty big deal. So, second part of your question is, what does it favor? Does it favor electrons or ions? This has been studied, in fact, by one of my students, Michael Rowan, did a thesis on reconnection and how it heats electrons and ions. This was done with Lorenzo Cironi when he was here as a postdoc. And what we can say is both ions and electrons do gain energy, probably at the ratio of 2:1 or 3:1. A little bit more goes into the ions, a little bit less goes into the electrons. But let me show a slide if I can. No, it doesn't want to go. Okay. Let me show this slide. This is the flow chart. So this is, the question is about this parameter delta, right? We have dissipated heat. And I said the fraction delta goes to the electrons, 1 minus delta goes to the ions. And the simple way to look at these models is to say this is lost. The 1 minus delta that goes to the ions just remains as heat. But the delta comes out as radiation. And so estimating this delta is highly important. And the reconnection work suggests that delta is less than 1 minus delta. But that's about all we can say. Maybe half of that, 1/3. And I should, in all honesty, say that in the early days when we did our first models, we used to assume that delta is tiny. We said it was 10 to the minus 3. We basically said energy goes proportional to mass. So since the electrons are 2,000 times less massive than the ions, we said 2,000 times less energy goes to the electrons. That clearly was wrong. I think the new current evidence is that it's more comparable. And I would say between 10 and 50% is in delta, and the rest is on 1 minus delta. So that was John's question. Did you have a follow-up on that, John?
No, that's a good answer. Thank you.
Okay. Janice Houston, Ichimaru. I was wondering about the Ichimaru paper and how you learned about it after it had been ignored in the 70s. Did it influence how you approached your work? Wonderful question. Okay, I can tell you the last bit. It did not influence our work because we didn't know it. We got all the key conceptual ideas on our own, had never heard of Ichimaru. And what happened was, and nobody else knew about Ichimaru, let's be honest, okay? Even the people who were publishing papers before us, they didn't know about Ichimaru. After we came out with our work, a year or so later, there was a conference, and I think this was in Reykjavik, Iceland. And, I went and did my spiel about, how these ADAFs are so great. They are the answer to our prayers and all that. And finally, during the conference summary, a distinguished person whom I will not name got up and basically did the big reveal. He basically said, this is all useless. It was all done by Ichimaru. Everybody knows Ichimaru. He did it 20 years ago, etc., etc. Well, after that, we started citing Ichimaru because, he did get many of the ideas. But yeah, I found out later, and, this is just what I heard. Martin Rees said Ichimaru actually visited Cambridge and gave a talk on this stuff. And Martin said he listened to the talk and he couldn't understand it. And if Martin doesn't understand, it means it was really poorly presented. That's my guess. It's probably the reason why nobody followed it up. But yeah, anyway, that's the story on Ichimaru. It has had no influence on our work, but it is true that they had anticipated many of the things that we came up with in 94, 95. Okay, next. Jack Steiner. Oh, our hero. Jack was a big part of the work that Jeff McClintock and I were kind of co-leading. Jack is thinking of the 50 black hole X-ray binaries that we have cataloged and wondering what would happen if a companion star over its magnetic cycle flips polarity when the system is quiescent and mad. Would this trigger an outburst, some sort of flare event that we might detect in the transition from mad to reversed mad? Actually, a very nice question. So it's a question of, Jack is asking about X-ray binaries, where you would think that this magnetic field has to come from the companion star. So Jack, you're right. In the simplest scenario, the field has to be supplied by the companion star and then transported by the accretion disk down to the black hole. And if the companion star flips, then suddenly it is supplying field with the opposite polarity, and that will come to the center. And when it reaches the center, it will start canceling what's already there. And then I feel we'll just go to the opposite direction and become mad again. So if this is the way it works, question is what happens during the interim? I don't know how long this interim will last, because I'm always reminded of the fact that you don't need a lot of flux. So my guess is it flips rather quickly, but during that interim period when it is flipping, the jet power will tend to go down. On the other hand, the jet may actually even become brighter because this flipping will allow more reconnection in the jet itself. This is what's called a striped wind or striped jet. And so it might even become a little brighter temporarily because it's dissipating more magnetic field into electrons. I don't know the answer, okay? So, but it is certainly true that it's not like these systems would be mad all the time. They will make switches. And if for some reason mad is difficult to reach, many of them may not be mad at all. I think that's unlikely. I'm going to assume that they're all mad, but they cannot be 100% mad. So they will switch. Would this be detectable? I don't know. I will make one other point, though. There is a beautiful piece of work done by Matthew Liska, who is a postdoc at the CFA. And he has done simulations in which he started with no net colloidal magnetic field. He put magnetic field only in the plane of the disk, completely toroidal, just in the phi direction. And then he kept running it. What he found was this guy, even though it had no net vertical field, automatically generated up and down fluctuations of the field, net zero. But in some region it will be pointed up, in some other region it will be pointed down. And then it continued accreting, and the guy became mad. So one of these patches of up-pointing field came around the black hole. That was enough to drive it to the mad state, and it was mad. And I think in his simulations, after a while, some other patch came. It flipped the polarity, so there was a little bit of confused period in between, and it went back to mad. So it almost feels to me like it doesn't matter what kind of gas you supply on the outside. The disk by itself will generate more than enough colloidal field to routinely send the system into this mad state. And then Jack's question would be how frequently would the flips happen? I don't know. This is where simulations will come in, and they will tell us what will be the statistics of these flips. How long will the system spend in the intermad stage? Yeah, these are all, I think, work to be done in the future.
Okay, I think, thank you, Ramesh. I think we're a little bit over time. Okay. It was a very enjoyable colloquium, and we're looking forward to an in-person colloquium again next week.
Okay.
Thanks, everybody.
Thank you, everyone. Bye.